So, good afternoon, everyone. This is Chaitanya Kumar, research scholar at IIT Madras in Department of Electrical Engineering. And today we are, so I will be taking your live sessions for problem solvings in basic electrical circuits NPTEL course. So it will be a 1 hour session, and I will try to keep it interactive. So I will request you people to keep pen and paper ready with you. I will present the question, give you around 5 minutes, and then you can solve those. After that, I will present the solution. So, okay, so the first question is there on your screen. Kindly take some time and try to solve this question. What is there in this question is that we have two current sources that are pushing in current into a capacitor, and waveforms of these current sources have been given in the question itself. What you need to do is you need to find the capacitor voltage on this at the time instance given, that is 6 microseconds. So kindly proceed with the question, and let me know if you come up with the answer in the chat box. Okay, so I will proceed with the solution of this. So, first of all, what we can do is we can add these two waveforms and make the overall calculate the waveform of overall current that is flowing into capacitor. Now, this can be done by Kirchhoff's current law. So since I1 and I2 are flowing directly into the capacitor, so the current of the capacitor is basically the addition of these two. So if we try to add this waveforms, it can be done as follows. So for time instance 0 to 1 second, the I1 is a flat waveform, and I2 is a constantly increasing waveform from 0 to 5 milliamps. And so at t equal to 0, due to I1 it will start from 5, and it will go all the way up to 10 till t equal to 1. And after that, since both I1 and I2 are constant, it will stay there at 10 milliamps till t equal to 2 seconds. And after that, there is a jump of 10 milliamps in I1. So since due to this jump, since the overall current is sitting at 10 milliamp at 2 seconds, it will go 10 milliamp below, that is at 0 milliamp. And after that, due to the constant decrease of I2, it will due to the constant decrease of I2, it will basically keep on reducing till -5. And so with this method, you can calculate the overall current waveform. And now the voltage across the capacitor that will develop due to this current will be basically the integral of the current that is flowing inside the capacitor. The integral is simply the area under the curve. So till 6 microseconds we need to find the area. So it can be found out piece by piece. So the first section, that is 0 to 1 second, is a trapezoid.
So can we do one thing?
Yeah.
From both of the curves, take the average current for the 6 microsecond period, integrate that current for 6 microseconds.
Yeah, so ultimately even if you have to take the average, you will have to integrate, take the area under the curve, right? So the amount of effort that you will have to put will be roughly the same. So yeah, you can do that. And yeah, so
Thank
okay.
you, sir.
So the other thing is that basically you need to find the area under the curve and then divide it by capacitance. It comes out to be 700 millivolts. So let's move on to the next question. So here is the question. Now in this question there is a parallel RLC network, and in this parallel RLC network there's a voltage source applied whose value keeps on changing, and its value is given in the graph mentioned here. And you need to find the current through the inductor and the voltage across the capacitor at time 3 milliseconds. So kindly try to solve this, and you can paste the answer depending on whatever option you feel it is right in the chat box. So let's proceed with the solution of this question. Now, since this is a parallel network, all the resistor, inductor, and capacitor are in parallel, so the voltage across it will be same. And so the capacitor voltage is straightforward. The capacitor voltage will be basically VC will be equal to the voltage that is applied across this network, that is Vx. And at time equal to 3 millisecond, its value will be 1 volt. Now to find the voltage across current through the inductor, what you need to do is you know that the current in an inductor is 1 upon L integral V dt, where VL is the voltage across the inductor. Now voltage across the inductor is also equal to Vx, and you need to integrate it from t equal to 0 till t equal to 3 milliseconds, and divided by the inductor to find the overall current that is flowing across through the inductor at t equal to 3 milliseconds. So for that, what you can do is this area under this curve, that is the triangle part, is half into the time, that is 10 to the power minus 3, into the voltage divided by the inductor, that is 10 to the power minus 3 again. And the area under the rectangle is length into breadth, that is 10 to the power minus 10 to the power minus 3 into 1 into 10 to the power minus 3. And as you can see, since these two areas are equal and opposite in fashion, so they will cancel each other, and hence you don't need to find their area. And yeah, so overall current that will be flowing in that in the inductor will be minus of 1.5 ampere. So D is the correct option. Now let's move on to the third question. So here is the graph of so there's a current waveform given in the graph in the question, and you need to find the average current in this waveform. So we will solve the question now. So now in order to find the average current, this particular waveform can be broken down into two parts. So you can see over here, this particular waveform is symmetrical about a line, and that line is the midpoint of 10 ampere and 5 ampere, that is 7.5 ampere. So there is a DC current portion of this, that is sitting at 7.5 ampere, and then there is a time varying current that is a rectangular waveform. So it goes 2.5 ampere in the positive direction. So it goes from minus 2.5 to 2.5 ampere in both positive and negative direction. Yeah. Now you can see that the area under the area under these triangles are equal and opposite. So the average of this particular component of the current is 0, and whatever remains is the DC value, that is equal to the average current of this waveform, that is 7.5 ampere. So this is how you go about solving this question. Okay, so let's move on to the next question. So what you need to do in this is, you have two current sources that are pushing or pulling out the current in this capacitor, and one of them is a DC current and other is a time varying current, and due to this you need to find the capacitor voltage that develops at t equal to 1 millisecond as well as t equal to 4 milliseconds. So let's proceed with this question. Now the resistor that is there in the series of this current source doesn't has any impact, as irrespective of this resistor, this current will flow in this capacitor. So now one thing that you can always keep in mind is that an element in the series of an ideal current source or an element so let's say we have an ideal current source that gives uh, some current as outputs across its terminal. Now, irrespective of any element in its series, the current that comes through this current source won't change. And similar is the case with an ideal voltage source. So let's say there is an element in the parallel of an ideal voltage source, it won't affect the voltage across this particular voltage source. So these two things you can keep in mind while solving these kind of questions. Now, apart from that, this the current that will flow into this will have two components. One is the I naught, and other is DC current that is of 1 milliampere. So, at 1 milliseconds, the current due to this time varying waveform will be the area under this curve till 1 millisecond, and that is equal to half into 10 to the power minus 3 into 10 to the power minus 3. So one is for milliseconds, other is for milliampere, and this will be divided by the total capacitance, that is 10 to the power minus 6 farads, that is 1 microfarad, and that is 0.5 volts. Now current due to the second component, that is the DC component, will be in the opposite direction, and that will be equal to minus of 1 milliampere, that is 10 to the power minus 3 into the time, that is again 1 milliampere, and that will be divided by the total capacitance, that is equal to minus of 1 volt. So the overall current that you get in this is equal to minus of 0.5 volts. Now for 4 milliseconds, now in case of 4 milliseconds, what you see is the overall current contribution due to I naught becomes 0, as the area above the time axis and below the time axis are equal. Hence the current becomes 0, and the only contribution will remain due to the DC current source of 1 milliampere. Now, if 1 milliampere current flows for 4 milliseconds in this capacitor, so the area under this curve will be 4 into 10 to the power minus 6, and that will be divided by the capacitance, that is 10 to the power minus 6, and this will give you voltage of minus 4 volts. Yeah, so this is about it. So let's go to the next question. Now in this question, what you need to find is so you have been given a VI characteristic of an element, and you need to find the small signal resistance at voltage of 1 volt and minus 1 volt, and the relation between V and I is given by I naught is equal to A times V mod of V, and A you need to find based on the two points that are given on this curve, and after that you need to find the derivative of dV by dIO. So let's proceed with this. Now what you need to keep in mind is that the modulus of V is equal to V for V greater than 0. For example, V is 1 volt, so its absolute value, that is the modulus, will also be equal to 1 volt. Hence modulus of V is equal to V, and modulus of V is equal to minus of V for V less than 0. So let's say the voltage is minus 1 volt. In that case, the modulus will be 1 volt. That will be minus of minus 1 volt. Okay. So based on this, the current can be written as follows. So for voltage greater than 0, your I naught will be equal to A times V square. Now if you put I naught equal to 1 milliamp and V is equal to 1 volt in this equation, you will get the value of A as 10 to the power minus 3. So the I naught overall can be written as this particular expression, that is for V greater than 0 it is 10 to the power minus 3 times V square, and for V less than 0 it's 10 to the power minus 3 times minus of 10 to the power minus 3 times V square. Now for V greater than 0, the derivative of I naught with respect to V is 2 into 10 to the power minus 3 volts, and what you need to find is the small signal resistance. So it will be reciprocal of the derivative, that is 1 upon 10 to the power minus 3, and at 1 upon 2 into 10 to the power minus 3 times V, and since you need to find voltage at 1 volt, so at 1 volt your the resistance at 1 volt, your resistance will be 500 ohm. And similarly you can find for V less than 0 also, and there also you will get a resistance of 500 ohm. So this is the last question for today, and in this basically what you need to do is you need to find the current through the inductor for the voltage, time varying voltage, that is whose curve is given as follows. You need to find the current through the inductor at t equal to 1 millisecond. So let's proceed. First of all, in the question itself, it's given that we can assume that the waveform between 0 to 1 millisecond is a sine wave. So now, as you can see, this is half part of the sine wave. So in ideal, sine wave goes something like this. So now the time axis, as you can see, is in milliseconds. So from here, and you know that sine within one cycle goes to 0 at time equal to at an argument of 0 and pi. So at t equal to 0 you have sine 0, and at t equal to 1 milliseconds you have sine pi, where this again goes to 0. So from this the what you can see is that your waveform from 0 to 1 milliseconds can be written as follows: pi into t into 10 to the power 3. So this 10 to the power 3 is to cover up for as the time axis is in milliseconds, and this pi will take care that the half time period of this particular sine wave is 1 millisecond. So what you need to do is you need to integrate this from 0 to 1 milliseconds, and let's say the area under this up to 1.5 milliseconds is A1. So you need to subtract this area, and if you divide it, you will get the incremental current from 0 to 1.5 milliseconds. Now one thing that you must keep in mind is that you have been given an initial condition over the inductor current, that is of 0.5 milliampere. So whatever this incremental current comes out to be, you need to add 0.5 milliamperes to this incremental current to get the actual value of the current, and then only like you will have the correct answer, or else you will get an answer that is 0.5 milliampere less than the actual one. So this was about it for today. Thank you for attending.
Thank you.